Number 7, integral from 0 to infinity, dx over x squared plus 2x plus 2. This is improper because this limit is infinite. The 0 is fine. All right. So here we can have an intuition. As x approaches infinity, our function 1 over x squared plus 2x plus 2 will behave very similarly to 1 over x squared. Okay? As x keeps getting bigger, imagine a billion squared versus 2 times 1 billion. A billion squared is much bigger than 2 times a billion. And of course, it's much bigger than a small 2. So that's why we say this guy starts behaving very similarly to 1 over x squared as x keeps getting bigger. Okay? And we know that integral from 1 to infinity 1 over x squared dx converges. So likely our guy here will converge as well. Okay, so I solved this in 2 ways. The first way, I did a comparison test. The second way, I actually directly evaluated this. It was actually pretty simple to evaluate. So let's go over the 2 methods. Method 1, comparison test. So the reason why you would want to do a comparison test is typically it's easier if you can find a function to compare it to. Okay, using our intuition, we want to pick something that's bigger that converges, okay? So what I'm saying in this blurb over here is that the bottom's not factorable. So if you don't like completing the square and all that, if you want to avoid that stuff, let's do a comparison test, okay? So for x is greater than or equal to 0, hopefully you would agree that 1 over x squared plus 2x plus 2 is less than or equal to 1 over x squared plus 2x plus 1. The denominator over on the left-hand side here is bigger, so we're going to be dividing by a bigger number, meaning our final value is smaller. Okay. This right-hand side, we can now factor as x plus 1 quantity squared. Okay. So what is this integral from 0 to infinity, 1 over x plus 1 quantity squared? If we evaluate it, it's 1. Okay. So since this guy converges, and our guy is even smaller, then our guy must converge as well by comparison test. Okay? This is one way we can compare. You could probably find a bunch of other functions that you can compare it to. This is how I thought to do it. Okay? Can you compare with 1 over x squared directly? You probably can. So you can probably do that as well. Okay? But here's just another option. Okay. Method 2, we directly evaluate. So I wrote it as the limit notation. So we got to complete the square. So x squared plus 2x plus 1 plus 1. I wrote it like that because the first 3 terms I can write as x plus 1 quantity squared. And here it is just arctangent if we do a little u sub. Okay, so it's arctangent of x plus 1. Evaluate from 0 to t. Fundamental theorem of calculus. Take the limit as t approaches infinity of this first guy is just pi over 2. This is a constant, so it'll just be whatever that value is, which is pi over 4. So our integral actually converges to pi over 4. We found exactly what it converges to. Okay, so here's 2 ways that we can approach this problem. Just directly evaluating, or we can do a comparison test.